Good afternoon, everyone. Physical AI and the next wave of physical AI and how we accelerate that. This is what I would like to share with you a bit, give you some insights. What do we actually mean when we talk about physical AI? Where are we coming from? What are the platforms to consider? And how can we apply that then in real-life applications? My name is Timo Kissner. I'm leading the manufacturing industrial business for NVIDIA in Europe, Middle East, and Africa. And let's start maybe with actually the previous waves of AI and where are we coming from. AlexNet in 2012, this was sort of the start where we realized, wait a second, there's a bit more to our GPUs than just visualization. Actually, you can do training and inferencing of AI models on those GPU. And this is where it really took off for us, not only focusing on visualization, but also really having a strong focus on AI. What we've seen and what every one of you has seen so far was a long phase of perception AI, speech recognition, understanding what's happening in images. And then all of a sudden, 2.5 years ago, generative AI was here. I guess everyone in this crowd is using Gen AI to the one or the other extent. It's part of our daily life. However, the question is, it's still limited in terms of the way we can interact with it. So a large language model gives you some very impressive capabilities, can interact with you, can give you a feedback, can give you an answer. However, if it's really about reasoning, well then we need to think about the next step, and that's when we talk about agentic AI. Using smaller models, combining them into workflows, and out of these workflows, all of a sudden we have very powerful AI tools, agentic AI tools, that not only help us solve a very specific task and very narrow and limited, but really can help us solve bigger applications and tasks overall. And now the next step is what we call physical AI. What do we mean by that? I touched upon large language models. What do you think? Large language models, pretty impressive, is it? Yeah? Pretty impressive what you can do with that. Agentic AI, same there. The one thing that those models are missing is spatial context. If you're using a large language model on your phone right now, well, you can interact with it, but it won't understand, doesn't have the understanding, where am I right now? What is the context that you actually need? And that is what we mean when we talk about physical AI. How can we combine the capabilities of a large language model or also any kind of vision model and then bring it into the context of the spatial environment, and with that really understand what is happening in this hall, in a warehousing environment, in a factory. That's what we talk about when we mean physical AI. And by the way, there is one important thing to keep in mind. When we talk about a virtual environment, physical AI means if an object goes around that corner over there and I don't see that person vanishing behind that corner anymore, it means physical AI understands that person is still there. It's not just vanished because it's around that corner. Physical AI understands that person is still there, and I need to still simulate and understand what is that person doing, or the AMR, the robot, whatever, to have the physical context of the space that we're talking about. So I already introduced a couple of the elements here. We see, for example, the large language model, which creates text tokens. We see image models that can create any kind of image token. We combine that into the physical AI model, and with that we are able to then cover many, many different use cases and applications in the virtual world. Now that will actually heavily influence all the industries, specifically manufacturing and warehousing from our perspective. Whether that's from a camera perspective, using cameras and integrating camera streams into your simulation environment, whether that's on factories, whether that's robots, whether that's warehousing, whether that's all the related supply chain, trucks, cars operations, all of that will get integrated. So everything will be influenced by physical AI. And what we actually need to consider, talking about physical AI and how we can address physical AI, are three different topics. We talked about the AI part of things already. Training a large language model, training your computer vision model, whatever that is, whether it's for quality control, for example, whether it's for safety applications in the factory. You need to have a certain environment where you train all those different kind of models. Now, on the other hand, well, you want to combine that with your virtual environment, with your digital twin, your physics-based digital twin. That's super important. We're not talking about any kind of digital twin, physics-based, based on the laws of physics, so very accurate, the perfect replica of your actual environment. So you want to combine those AI models with that physics-based environment, and ultimately you want to run those models on any kind of intelligent machine, any kind of robot. And that's exactly where we as NVIDIA provide the respective infrastructure for that, ecosystem around that to actually enable those physical AI workloads. Two threads to consider. One, what we call inside-out AI, so a simulation environment that you can leverage to do all the training of your AI models to then deploy it in the real world without any delay, so no going back and forth between your robot and your computer where you need to train it, but you can right away deploy that after you train that, versus outside-in AI, understanding using video analytics AI agents and combining that with your actual virtual environment. I already mentioned the ecosystem. Now, if you are like, awesome, I need that. Let's do that right away. What do I need? How do I do that? Well, this is what you need. Think of physical AI, physics-based simulations. Think of an ecosystem play. And it's not like, here are the providers, whether that's robot simulation software, whether that's enterprise software, the actual sensor and robotic makers. It's about you. If you want to have a physics-based digital representation, if you want to use physical AI in your environment, this is where you need to contribute. You are part of that ecosystem. An actual implementation will not happen just by you doing something or just by the ecosystem leveraging something. It's about leveraging the data that you have, applying that data, and developing your environment using that ecosystem. So from our perspective, and that's, by the way, a very integral part, I would say, of how NVIDIA is working, everything that we do is always in an ecosystem. We are just providing the platform, we are providing the compute infrastructure, we are providing the platform above that you can then leverage to build your use cases on top, but it's all around an ecosystem. Now, let's dive into those two threads, inside-out AI, outside-in AI. You might have heard of our Omniverse platform, and that's very important. Omniverse is a platform. It's not a solution. It's not an application. Omniverse is a platform for collaboration and development. You can build your own applications on top of that. So what it is, from a very technical perspective, it's a combination of APIs, services, and SDKs that you can leverage to build your use cases on that platform. And again, it's the ecosystem. It's the ecosystem of all those players that you saw before, combining all their knowledge and bringing it into one space. Now, there is one crucial element, and you see it on the upper right-hand side where it says OpenUSD. Who of you has heard of USD? Not so many? All right, I'll talk about USD. USD stands for Universal Scene Description. What it is, basically, it's a format to describe 3D scenes, 3D formats, 3D worlds. The difference, though, is, well, we have many different 3D formats out there. The difference with USD is you can combine any kind of data with USD. So it's not only about the actual 3D asset, it's about combining any kind of environmental data, any kind of metadata, process parameter with your 3D asset. Now let me jump to the next slide so that we have a bit of a visual here. What you see here is only, well, able to do that, we are only able to do that on the basis of USD. Why is that? Because we can combine all kind of different data sources. And keep in mind, any kind of environmental parameter, not only 3D, but you can combine that with any kind of process data. So what USD is actually doing, it's providing a standard format where you can then tap into any kind of tool, any kind of data source that you are already using today in your PLM process, in your planning process for your factory, in your development process for your products. You can use all those different tools, all the different outputs of those tools, transfer it into USD, and then with a layered approach, we're able to create that scene over there. Now, the question always is, and always comes up, no, let me quickly finish on USD and why we say open USD. Initially, that started as a proprietary format developed by Pixar. Today, it's an open format. There is an association behind that. Many partners, including industrial partners, working on OpenUSD, developing it further. There are industrial work streams to make it also very applicable for manufacturers. So that is the core of what we see here. The important piece now is really that we combine all the different data sources, bring that into one place, and with that are able to create that full fidelity visualization. We're talking about full fidelity visualization in that case, but keep in mind, don't think of it, yeah, sure, NVIDIA, 3D, photorealistic in real time. No, that's just one part of full fidelity visualization. Full fidelity means the combination with any kind of processed data. So what you see here is not just 3D photorealistic. What you see here is the combination with any kind of data, and any kind depends on what you want to actually put into that digital twin, into that physics-based digital twin. Any kind of process parameters from the actual shop floor. And with that, you get the perfect replica as a starting base to do what? Well, to train your physical AI models. And by the way, that's the reason why this also needs to be photorealistic. You want to train your sensors of your robot, you want to train your whatever camera for a safety application, well, you for sure don't want to train that in a low fidelity environment. You want to train that in exactly an environment where it looks 100% like what that sensor would see in the actual real facility. So that's the reason why that needs to be photorealistic, right? And in 3D, so that you can train any kind of physical AI application there. Now, the question, of course, is always like, well, what's the benefit? I mean, come on, yeah, I get it. It's the start, like, do you have some numbers? We do have some numbers. 30% planning efficiency, and I won't walk you through all those examples now in detail, but 30% planning efficiency for a new factory. I mean, 30% of your factory planners being able to spend on additional optimization. That is quite something. Foxconn talking about 30% energy savings using Omniverse in planning new production lines. Continental talking about 10% productivity gain using those different data sources. Think about it, combining all kind of different data sources into one physics-based digital twin that you can then leverage to train any kind of AI model on top of that. Kio and I will come back to that. So this is what I wanted to share in terms of the outside-in AI perspective. Inside out, now that's the other way around. So we do have a camera stream, and without going too much into the details of that architectural drawing here on the right-hand side, well, it's basically around, we have a video stream, we chunk it into different sizes, we analyze that material, and we combine it with a RAG use case behind so that I can use my large language model to then tap into, and that's what you see over here, tap into that video stream and understand, for example, like what is actually happening there, what happened at a very specific point in time. I don't need to go through that full video to see what happened, but the large language model, the video language model, gives me the feedback of what actually happened. And now if you think of combining the physics-based digital twin with this tool, this is going to give you a very powerful environment to work in. And the way this looks like, we're going to have a look at this video.
Kion, the supply chain solution company, Accenture, a global leader in professional services, and NVIDIA are bringing physical AI to the $1 trillion warehouse and distribution center market. Managing high-performance warehouse logistics involves navigating a complex web of decisions influenced by constantly shifting variables. These include daily and seasonal demand changes, space constraints, workforce availability, and the integration of diverse robotic and automated systems. And predicting operational KPIs of a physical warehouse is nearly impossible today. To tackle these challenges, Kion is adopting Mega, an NVIDIA Omniverse blueprint for building industrial digital twins to test and optimize robotic fleets. First, Kion's warehouse management solution assigns tasks to the industrial AI brains in the digital twin, such as moving a load from a buffer location to a shuttle storage solution. The robot's brains are in a simulation of a physical warehouse, digitalized into Omniverse using OpenUSD connectors to aggregate CAD, video and image to 3D, LiDAR to point cloud, and AI-generated data. The fleet of robots execute tasks by perceiving and reasoning about their Omniverse digital twin environment, planning their next motion and acting. The robot brains can see the resulting state through sensor simulations and decide their next action. The loop continues while Mega precisely tracks the state of everything in the digital twin. Now, Kion can simulate infinite scenarios at scale while measuring operational KPIs, such as throughput, efficiency, and utilization, all before deploying changes to the physical warehouse. Together with NVIDIA, Kion and Accenture are reinventing industrial autonomy.
All right, so we talked about physics-based digital twins, we talked about AI. Let's briefly look into robotics. We see a fundamental change in robotics, going from specialist, pre-programmed robotics tasks to very flexible generalist robotics applications. And whether that's now a humanoid robot or some other kind of implementation, that's, I think, not the question that we should discuss here. The core of it is that if you look at, and well, in that example, we stick to the humanoid robots. If you want to test those robots and develop them to a point in time where you are ready to deploy them, well, that's quite an effort. And hey, do you really want to spend that much money to have quite a couple of prototypes being damaged? Probably not. You want to do that in the virtual world, and this is exactly where you would start with that Omniverse platform again. Now, the next step for us is actually we are providing a platform which we call Isaac GR00T that helps humanoid developers to do exactly that. Building on top of what we discussed before, physical AI, we call it World Foundation Model, a model that helps you create thousands, 10,000s of scenarios out of one starting point in your physics-based digital twin. And by the way, if you're using that for robotics development or using that for warehouse optimization, that doesn't matter. Yeah, that's just an example over here. Synthetic motion and data generation pipelines, tools to train your specific application. This is what we're having a focus on. And again, this is where, think of those three computers, those three problems that we talked about: AI, the virtual environment, and the robotics application, the actual robotics application. This is where it all comes together. And also in that environment, of course, we're talking about a developer ecosystem. This is not something that NVIDIA solves now. This is not where an individual robotic player has all the answers. This is where we need to play this ecosystem. And again, this is where you come in with your environments that then help the robotics developers to understand what does my customer, what does my partner actually need, and how can I train my robot in that virtual environment. With that, I would like to wrap up and show you a last video.
For 60 years, Software 1.0, code written by programmers, ran on general-purpose CPUs. Then, Software 2.0 arrived, machine learning neural networks running on GPUs. This led to the big bang of generative AI, models that learn and generate anything. Today, generative AI is revolutionizing $100 trillion in industries. Knowledge enterprises use agentic AI to automate digital work.
Hello, I'm James, a digital human.
Industrial enterprises use physical AI to automate physical work. Physical AI embodies robots like self-driving cars that safely navigate the real world, manipulators that perform complex industrial tasks, and humanoid robots who work collaboratively alongside us. plants and factories will be embodied by physical AI, capable of monitoring and adjusting its operations, or speaking to us. NVIDIA builds 3 computers to enable developers to create physical AI. The models are first trained on DGX. Then, the AI is fine-tuned and tested using reinforcement learning physics feedback in Omniverse. And the trained AI runs on NVIDIA Jetson AGX robotics computers. NVIDIA Omniverse is a physics-based operating system for physical AI simulation. Robots learn and fine-tune their skills in Isaac Lab, a robot gym built on Omniverse. This is just one robot. Future factories will orchestrate teams of robots and monitor entire operations through thousands of sensors. For factory digital twins, they use an Omniverse blueprint called Mega. With Mega, the factory digital twin is populated with virtual robots and their AI models, the robots' brains. The robots execute a task by perceiving their environment, reasoning, planning their next motion, and finally converting it to actions. These actions are simulated in the environment by the world simulator in Omniverse, and the results are perceived by the robot brains through Omniverse sensor simulation. Based on the sensor simulations, the robot brains decide the next action, and the loop continues, while Mega precisely tracks the state and position of everything in the factory digital twin. This software-in-the-loop testing brings software-defined processes to physical spaces and embodiments, letting industrial enterprises simulate and validate changes in an Omniverse digital twin before deploying to the physical world, saving massive risk and cost. The era of physical AI is here, transforming the world's heavy industries and robotics.
All right. So with that, I hope I could give you some, glimpse of where we are heading, some inspiration, hopefully, of what could be of interest for you. We do have a couple of NVIDIA colleagues right here in the theater, so feel free to approach us, ask any questions. I will be here at the stage for another 10 minutes. Feel free to come here. Apart from that, we're having a small kiosk just here at the AWS booth around the corner. Thank you for your attention.